This is a cubic polynomial function, so we have a good idea what this is going to look like. It's going to be a positive one that looks like that. So the first thing we'll do is we'll factor this, and we'll factor this to find some zeros. So we get f of x is equal to, there's a greatest common factor of x, and then we're left with the quadratic x squared plus 3x minus 9. Now that's not factorable, so I'm just going to start a table of values over here. So I have a 0 at 0. Okay, then I'm going to look for some other zeros by solving this quadratic. I have to use a quadratic formula, so I'm going to get negative 3 plus minus the square root of 3 squared minus 4a times c. And that's all over 2a, so that's all over 2. So when I simplify this, I get negative 3 plus minus square root. That's going to be positive 36, so plus 9 is 45 over 2. And that will simplify if we want to. We don't have to simplify the radical, but we end up with 3 root 5 over 2. Okay, that works out to be approximately, looks like 1.85 and negative 4.85. Okay, so I'm going to just draw in some points here. So there's going to be a point here, maybe somewhere around here, and 1.85 maybe somewhere around here. Okay, so those are going to be my zeros. So I'm going to put a negative 4.85, 0, and looks like about 1.85. There's my 0. Okay, so I've got all the stuff I normally would have. I've got my y-intercept, which is one of my zeros. I've got my zeros. Now I want to find min and max points. So I want to use the derivative. So I'm going to differentiate the original function. So I use power rule, 3x squared plus 4x minus 9. Sorry, that's going to be 6x, sorry. 6x minus 9. I'm going to factor out the greatest common factor before I solve this quadratic. And it looks like this is factorable. So this becomes x plus 3, x minus 1. Okay, so this gives me some points to work with. So I know I have a min or max at negative 3, and I have one at positive 1. So I have 0 slopes there. So I should test my slopes. F prime at negative 4. When I plug negative 4 in here, I'm going to end up with, looks like positive slope. So it's going to be 48 minus 24. Yeah, that's going to be positive. So I have positive slope out here. That must be a max. Okay, f prime. We kind of know this already because we know the shape of this polynomial. But we're going to just show our test anyways. So plug in a 0. If I put 0 in, I get negative slope through here. That's a minimum. And then at f prime, at positive 2, plugging positive 2 into here, we're going to end up with positive slope. So there's my slope chart. Okay, so I have a good idea what this looks like. I should find my min and max coordinates at 1. I should move this over a little bit. At x equals 1, I need to plug in. So x equals 1. I plug into my original function. I get 1 plus 3 minus 9. So that's going to be at negative 5. So at 1, negative 5, I'm going to have a minimum point. Okay, my maximum point is going to happen at negative 3. So I plug negative 3 into this. So I get negative 27 plus 3 times 9 is positive 27, so that's 0. And then negative 9 times negative 3 is positive 27. Okay, so at negative 3, positive 27, that looks like it's going to be somewhere around here. I'm going to have my max point. Okay, and I want inflection point, so I'm going to need a second derivative here. So I know an inflection point is somewhere in here, so differentiating this polynomial. The nice thing about polynomials is that they get to be lower degree every time I differentiate. So I get 6x plus 6. My f double prime is equal to 0 at x equals negative 1. So at negative 1, I'm going to have an inflection point. Okay, well, we don't know that for sure until we test the actual derivatives. So we're going to test f double prime at negative 2. When we plug that in, I end up with a negative concavity, so negative value, so that means it's a negative concavity. And again, my slope chart confirms that. And then at f double prime, we're going to choose some point on the right-hand side of negative 1, plug in 0, we end up with plus 6. So we end up with a positive concavity on this side. And again, our slope chart confirms that, but now we have shown that there is a change in concavity across negative 1. So we know that that must be an inflection point. So I'm going to plug in negative 1 into my table. So negative 1, if I plug that into f of x, I get negative 1 plus 3 plus 12. Okay, so that's going to be negative 1 plus 3 is 2 plus 9 is going to give me positive 11. Okay, so negative 1, positive 11, maybe somewhere around there, and that represents my inflection point. Okay, just want to double check that calculation. Negative 1 plus 3 is plus 2. Negative 1 and 9 is plus 9, so that gives me plus 11. So that's correct. So there's the points I'm going to use to draw this. And the nice thing is we do know what polynomial functions look like. It's going to go through that 0. It's going to have a maximum here. At that green point, that's my inflection point. So I'm going to change concavity from concave down, go through my zeros, my min point, 0, and then it's going to go off like that. So there is all the parts to help me draw the polynomial function. We kind of know what this looks like, but this is all the work to confirm some of the points that we kind of knew were already there.